In this video you will learn why position and motion cannot both be known exactly. We start with a simple microscope thought experiment. Imagine shining a flash of light on a tiny moving particle to see where it is. If the light has a long wavelength, the picture is blurry, so the particle's position is uncertain. If we switch to a very short wavelength, the light can pinpoint the particle more precisely. But each photon carries more energy, and when it hits the particle it gives it a jolt that changes its momentum. Thus, the better we know the position, the more we disturb the momentum, and vice versa. Now picture the particle as a wave packet, a localized bump made of many sine waves. When the packet travels, it spreads out, showing that the particle's location becomes fuzzier over time. This spreading is a visual representation of wave-particle duality. The quantitative rule that captures this trade-off is the uncertainty inequality. Delta x is the standard deviation of the position distribution. Delta p is the standard deviation of the momentum distribution. And h bar is the reduced Planck constant, about 1.054 times 10 to the minus 34 joules-second. A graph of a Gaussian wave packet illustrates the principle. When the position curve is narrow, the momentum curve is wide. And when the position curve is wide, the momentum curve narrows. Let us work through a concrete example. Suppose an electron is confined inside a box that is 1 nanometer wide. We take delta x to be roughly 1 nanometer. Using the inequality, we estimate delta p as h bar divided by 2 times delta x. Plugging the numbers gives delta p about 5.3 times 10 to the minus 24 kilogram meter per second. To get an energy estimate, we use kinetic energy equals delta p squared divided by 2 times the electron mass. The electron mass is 9.11 times 10 to the minus 31 kilogram. Carrying out the calculation yields a kinetic energy on the order of a few electron volts. Showing that confinement forces the electron to have a noticeable motion. It is important to stress that this uncertainty is not a limitation of our measuring tools. It is an intrinsic property of quantum systems. The particle simply does not have a simultaneously sharp position and momentum. Finally, consider real-world implications. Electron microscopes use short wavelength electrons to resolve tiny features. But the uncertainty principle sets a limit on focus. Similarly, the stability of atoms relies on the balance between confinement and kinetic energy dictated by the uncertainty principle. By understanding this principle, you now see why the quantum world behaves differently from everyday experience, and why precise knowledge of both location and motion remains fundamentally out of reach. Generate your own educational videos for free at eduvids.vercel.app.